All right. Good morning. Thanks for joining. I really appreciate it. Welcome to the session on From Functional to Reactive Programming. My name is Venkat Subramaniam, and I'm going to talk about my journey towards reactive programming and what did I learn along the way, and some reflections on what it means to me. Best time to ask questions or make comments is anytime you have it. Please post your questions on the Q&A, and I'll try to answer them along the way. I'm not going to wait till the end to take the questions. So anytime along the way is a great time for you to post questions. I'll be delighted to answer your questions if you have any. So with that said, let's get started. Well, when it comes to programming, especially reactive programming, I often wondered, why do we need yet another programming model? Well, it turns out reactive programming is not entirely new. Well, the term was coined relatively, recently compared to the history of programming, but in a sense that we've been doing reactive programming for a few decades. But nevertheless, it is really gaining a lot of popularity in recent years. And what are some of the reasons for it? And as I was struggling to really understand what reactive programming, is, I'm a person who is deep down at a code level. I'm a programmer. And when I see things in code, I understand. When people talk about concepts in general, I get a little frustrated because I'm not really a fan of hand waving. I really want to get to the nuts and bolts of things and really understand how to use things and how to be effective with those things. So as I was struggling with understanding reactive programming, I came along with the background of functional programming a few years before that. Well, in my life, I would say I've gone through, maybe about, I'm going to say 6 different paradigm shifts. Well, learning to program itself was a very first one. And once I started to learn programming and realized that I could make computers do things, that was an aha moment for me. Then I, of course, learned structural programming, working in languages like Fortran and C and such languages. Then I focused on the next big transition for me was object-oriented programming. And that took a while to grasp, to understand polymorphism and how that actually works towards creating extensible code, took quite a bit of an effort. Once I really understood object-oriented programming, the next big fog that I really came across that took a lot more effort was really the times of COM and CORBA, and understanding distributed object computing, not just object-oriented programming. And that was really hard because to understand, well, writing code was not really hard in distributed computing for me, but understanding how it actually worked and all these discussions about the factory methods that would bring a remote object to your presence, that was really confusing until I really understood how that was working. Once I got past the distributed object computing, my next big, transition for me was, in all honesty, understanding asynchronous programming. This was really frustrating for me to learn JavaScript. Don't get me wrong, JavaScript as a language was not really hard for me, but really understanding how to program on the node and how to do asynchrony took me quite an effort to understand how to do asynchronous operations. And once I really understood asynchronous programming, the next real hurdle for me was understanding functional programming. And what made it worse was people around me would say, oh, that's really easy. But no, I came from decades of programming in the imperative style. How in the world do I think functionally and program it? And so that was the next transition. And then, of course, when I thought I was done, I came across reactive programming. And here we go again. I've got to learn yet another paradigm of programming. Well, as I was going through the journey of programming with reactive applications, I was really struggling to relate this back to things I already know and see the similarities and differences. And that's basically what I want to focus on today in this presentation. Let's step back a little bit and talk about what is really functional programming, because after all, my topic here is from functional to reactive programming. So let's just root our grounds a little bit on functional programming. Well, when it comes to programming, we all of us have done imperative style of programming. And imperative style is where we tell what to do and also how to do it. So that's basically what we do in the imperative style of programming. Well, on the other hand, in the declarative style of programming, we tell what to do, of course. In both of those we do, but not how to do it. So in a sense, in the declarative programming style, we focus on the what and leave it to the underlying libraries to really do things for us. And we rely upon a higher level of abstraction when it comes to programming in the declarative style. Well, that kind of begs the question, what in the world then is functional style of programming? Well, my first realization as I was programming in functional style, like I said, I'm a person who gets really unhappy if I don't understand and cannot relate to things in a way that makes me really comfortable saying, yep, I think I can handle that. So when I was really going through functional style of programming, I was trying to explain what that really means. And my understanding really evolved to the following: that functional style of programming is equal to declarative style plus the use of higher order functions. So that's basically what it boils down to. Programming in functional style is a mixture of declarative style and the use of higher order functions to be able to achieve this. So that's one of the nice things about functional style of programming, is because it's declarative, it lowers the accidental complexity and makes it a lot easier for us to understand, work with the code, and maintain it as well. So, but having said that, what is really essential to functional programming? Now, I'm sure a lot of us have heard this over and over and over from a lot of people who talk about functional programming, including myself, how immutability is so important. And over the years, I've realized that's really not a good way to neither teach nor learn functional programming, because telling developers not to mutate variables is like telling children to eat vegetables. No wonder they don't really like it. So we need to really bring together the reasons why we want to really honor that, not as a primary, not because it's fashionable, but because it's got consequences to what we do. So in that regard, I'm going to say that real essence of functional programming really comes down to two things. Functional programming is, now if I were to ask you what is really about object-oriented programming, sure, there's abstraction, sure, there's encapsulation, and sure, there's the weakest link called inheritance. But the real essence of object-oriented programming is polymorphism, which leads to extensibility. And that is what we really focus on, because polymorphism, if you will, a polymorphism leads to extensibility, and that is why it's so central to object-oriented programming. And in the same way, in functional programming, it is really a combination of two things. One is the functional composition plus the use of lazy evaluation. So I'm going to say that polymorphism is to as lazy evaluation is to functional programming. And that is one of the key reasons why lazy evaluation plays a very central role. But why is it so important to really focus on laziness? And the reason is, like we talked about here, polymorphism leads to extensibility. Lazy evaluation, lazy evaluation, literally by facilitating that, functional programming makes it possible to get efficiency of code execution. So lazy evaluation leads to, if you will, leads to efficiency. So that's one of the really important reasons why we favor lazy evaluation. Without lazy evaluation, we wouldn't be talking about functional programming after all. So lazy evaluation leads to efficiency along the way. So that's basically extremely important for us to be able to accommodate. So take away polymorphism, there is not a whole lot of OOP, and take away lazy evaluation, there is not a whole lot of functional programming as well. So what is functional composition and what is lazy evaluation? Well, let's quickly take a look at one little example to play with this. Let's say for a minute that we create a function right now, we'll call it Boolean is even, which takes a number, and all it's going to do is simply return, let's say, the number mod 2 is equal to 0. Well, that was a very simple function called is even. Let's also create one other function. We'll simply say, we'll call it as a double it function right here. And the double it function is going to return the given number n times 2, if you will. Well, given these two values, let's take a collection of numbers to work with. So I'm going to say numbers is equal to list of, well, let's take a list of numbers here, if you will, 1 to 10, and we can say dot filter. Well, we can get an internal iterator, and we can do a filter on it, and we can say sample is even. We can perform a map of the double it, if you will. And then after this, of course, we could say for each, and we can simply do system.out and print line, and we can print it. Now, when we look at this particular example, what are we really achieving in this particular case? Well, what we are doing in this case is we are asking it to create a list of integer values, and we are asking it to iterate over these numbers. Obviously, I'm not saving the result back into it, so that was giving me an error. So you can see in this case, it was iterating and printing the double of even numbers. Now, clearly, right there is the functional composition we see. So in a way, if you really think about it in functional programming, think of this like water that flows through a filter, that flows through a cooler. And then, of course, once the water flows through a cooler, you get the water and you can use it for whatever purpose you want. Maybe it comes out of a refrigerator or fridge. Or similarly, in a Unix pipeline, you could say cat, some file input.txt, if you will. So we could say input.txt, and we could do a grep on something that you are interested, and we could do a word count on it. That's an example, again, of a pipeline of operation. Well, Martin Fowler calls this as the collection pipeline pattern. So the structure we see here is this pipeline of operation that flows through in functional programming. So essentially, that's our functional composition that's part of the functional programming. However, if you take this particular example, and if we were to say result is equal to, and then back in here, I'm going to simply say dot find the first, and I want to really output the first value. Let's say output the result, or else if it doesn't exist, give me a 0. That's perfectly fine. Now, if you look at this, it gave us a result of 4 because the first number that's an even number is 2, and the double of 2 is 4. So we got the result of 4. Now, we could have gone ahead and written something along the lines of maybe 1, 1, 1 a few times here. Now, in all these cases, of course, the result is still a 4. But the most important point is we could have had many more numbers sitting here, if you will, after this number. And this could be going on for a long time. But the point is we don't want to do any extra work. So if this code were to really process every single element in this collection, find if every one of them is even, double each of them, only to throw away almost all of them and get one of the earlier values, that would be really inefficient. Well, here's the charm. If I go back to this code and say output, let's say is even called for, and I'm going to say the number n, and I'm going to go ahead and say this is going to be double it called for the number n. When I run the code this time, notice how the double it was called only for 2. It never touched the values 4, 6, 8, 10, and so on. Well, that's because of lazy evaluation. So lazy evaluation says, I don't need to evaluate the filter and the map operations until that is being done on demand when the find first function says, give me the elements, and when you got the first element, stop it, I don't want it anymore, and it can quit. So in other words, the computation is lazy, as in it postpones evaluation until it can no longer postpone it. And that's one of the biggest benefits we get out of lazy evaluation is efficiency. In fact, let's go back a little bit further with this. Suppose we go back to this code right here. Let's not worry about storing the result right now. And I'm going to go ahead and say output done. And when I execute the code, you can see that it printed all of that and said done. However, If I comment out just the last line, the find first alone, and execute the code, you can see that it simply said done. It did not waste the time or the effort performing the filter on the map. Even though those two are present in the code, they were totally skipped over. And the reason for that is lazy evaluation. So essentially, lazy evaluation is extremely fundamental for efficiency. And without lazy evaluation, we will not have efficiency in functional programming, and we wouldn't be talking about it. Don't assume all languages that support functional style of programming provide lazy evaluation. Some don't do, and a lot of them don't. And so we need to really pay attention to it. So to summarize what we talked about here, I'm going to say efficiency is attained not by doing things faster, but by avoiding things that should not be done in the first place. So if you want efficiency, don't look for speed, but look for avoiding work that shouldn't be done in the first place. So how can you make this more efficient rather than faster in the long run? You know, I live in the bear country, and people often talk about, if you're going to go on a hike on the mountain, what if there's a bear coming your way? You know, I used to be really scared about it in the past. Then somebody wise advised me, and they said, oh, Venkat, you don't have to worry about bears as much. And I said, my gosh, what do I do? And they said, you don't have to really run fast when you see a bear. You just have to run faster than the person behind you, they said. Well, that's efficiency, isn't it? No, just kidding, for two reasons. One is that's really mean to say it. But second, you shouldn't be running if you see a bear. That's usually the advice they give you. But anyway, coming back to the topic, we want to really focus on efficiency, and efficiency is attained by lazy evaluation. Now, remember why functional programming emphasizes immutability, because in the presence of mutability, it matters when we execute a piece of code. We cannot defer the evaluation. So that is why immutability is so important, because without immutability, laziness is not possible. And without laziness, efficiency is not possible in functional programming. So that's basically where I'm going to stop talking about functional programming and then move on to talk about reactive programming from then on, and see what that really means and how we can relate these concepts together. But I want to just quickly yield and see if there are any questions or comments. You're most welcome to post your questions on the Q&A. You can post them with your name on it. You can post them as anonymous, whatever makes sense for you to do. I'll be delighted to hear your questions or comments. If you don't have any questions, you can even post to see if you are able to hear my audio properly, see my video. Some kind of a feedback is actually very helpful as a speaker, because otherwise I'm speaking to a brick wall, and that's not fun at all. So post some questions, comments. If you find something is really funny, you can post aha on it as well. Just keep the feedback loop going. After all, we humans are really thriving on feedback. So please use the Q&A to post something. If you have any question or a comment, I'll definitely welcome that if you want to participate doing that. So with that said, we talked about the functional programming, and the efficiency is so important. Thank you, Ben. Appreciate it. So that's basically where we are looking at efficiency coming through as a very important means to functional programming. So with that said, let's talk about essentially, what is reactive programming? So when I got into reactive programming, I was really, frustrated. And the reason for the frustration was to understand why we need yet another programming paradigm. What is the reason for it? And it turned out that this has been around for a very long time. So reactive programming, the term was coined by Eric Meyer as part of his work in Microsoft Research. But had he thought about it a little bit, maybe he would have called it a little bit different. You see, the word reactive he used, and the word reactive he used to represent the true meaning of the word reactive, which is to respond to stimuli. But had he thought about it, Well, in American English, the word reactive has a bit of a negative connotation. You don't want to go to somebody and say you're a reactive person, right? Because they want to be told you're a proactive person. Well, had he named it proactive programming rather than reactive programming, maybe would have had a lot more excitement around this. But this has been around for a while, I was mentioning, but I'll give you two examples of reactive applications. Applications that can respond to stimuli, but can also grow to the scale. Now, when I started programming decades ago, the type of applications that I built were very different from the type of applications we build today. Now, if you go back in time, and to be fair, we still do this today as well, we can summarize what we do into an acronym, isn't it? Which is CRUD. A lot of us have developed CRUD applications. So we take the data from a database and we do some processing of the data, and then we typically put that back into the database. You know, try explaining this to the grandparents. They ask you, what do you do for a living? And you're trying to struggle to say what to say. And then you say, you know what, grandparent? You say, I take the data from a database, from where it's sitting, I do some work with it, and I put it back where it came from. And they look at you and say, and you go to work for doing that? And that's kind of boring, isn't it? Where you take the data and you put it back where it came from, what's the point in doing it? But that's what we have been doing for a long time, is do these databases. But this was before the time of big data, which really means two things to me. One is high volume data, or it also is high frequency data. The data may not be large, but we get a lot of data over a period of time. Or the data could be really large as well, and both of those could be scenarios we often want to work with. Now, in that regard, if you really think about this, dealing with a large volume of data or high frequency of data, and to be able to respond to it very quickly, responsiveness being very important criteria, is where reactive programming really focuses on. But I was mentioning that this has been around for a very long time. I'll give you examples of two applications that I squarely think are primary examples of reactive programming. One of them, which has been around for a very long time, and maybe arguably we could say the best application humans have ever created, hands down. You know what I'm talking about, right? Microsoft Excel. I don't think there is any application that competes to it, in my opinion, because Microsoft Excel is pervasive. It is everywhere you see it. The concepts are so prevalent. You see people of all walks of life use Microsoft Excel. Well, with Excel, not only do you have spreadsheets, but you have many, many spreadsheets. But you could be modifying a cell over here, and before you could blink your eyes, as you hit the tab or click elsewhere, all the cells that depend on the cell immediately update. And those cells that depend on those cells in return get updated, and the change ripples through the spreadsheets instantaneously. That's an example of being reactive. Now, you may look at me and say, gosh, that's been around for a very long time. Oh, yeah. Reactive applications have been around for a very long time. We just didn't give them the name until very recently for that. But another example of this is almost thing that really dawned on me is I travel a lot. I'm in different parts of the world constantly. Well, when I was in one part of the world, a remote part of the world one day, well, because I traveled so much, I share electronic documents with my family. And in all honesty, because of my nomadic life that I live, my family and I exchange a lot of information through Google Docs. You know, my children would update Google Docs. I would asynchronously review those documents, update them for them to see. And so a lot of our communication happens asynchronously. But on one of those trips, I was in some remote part of the world, and I logged into the Google Docs one morning, and it was early morning for me, you know, late afternoon for my wife. And I realized that she was actually updating the document exactly at the same time. So I scrolled down all the way to where she was editing, and I could actually see on my screen the edits that she was doing and the cursor moving forward. And I put my cursor exactly where her cursor was, and I started changing the text that she was changing. And for her to stop typing and then to type, "Get out of my document now," was absolutely priceless. And I sat back and thought about it, and I said, oh my goodness, this is the most fantastic use of reactive programming. The ability for someone to be thousands of miles away and yet find a way to annoy their spouse. I mean, what else could be a better application of technology? So I sat down and thought about it and said, my goodness, if you really think about it, in this particular example, it was my wife and I editing the document. But a lot of times I've got, 10, 15, 20, sometimes 100 people editing exactly the same document when I'm part of, helping a conference organizer as a conference, a program committee member, or I am reviewing some other proposals. We are editing documents at the same time. But any given time, millions of people are using Google Documents. Hopefully not exactly the same document, but the point is millions of people are using Google Docs exactly the same time. And I couldn't think of a better example of a reactive application at that moment. So reactive applications are really about high volume or high frequency, and they have to respond to stimuli almost continuously. And that's really the modern application we are focused on. But why do we need a different programming model? Well, as it turns out, it's not a really new or a different programming model. In a way, I would say reactive programming is a lot like extreme programming. You remember, extreme programming did not bring in anything new at all. And yet, what was new in extreme programming was the emphasis on the 12 practices that it really wanted to promote. So extreme programming was a packaging of 12 pre-existing practices with really good emphasis. In a similar way, the concept behind reactive programming is to bring 4 practices that exist already, but with greater emphasis towards them. So in terms of building the applications, how does it really help us? We'll talk about what those 4 are a little bit later. So given that, we want to really focus on building these reactive applications. So like I mentioned, we lived in the world of CRUD, but what are we really heading? Well, if you have lived in the let's say 80s, you could not have survived the late 80s and early 90s without hearing the words called data flow computing. This was huge back in time. Some of you probably are very young and you're wondering, what is this old guy talking about? Some of you are probably much, older, and you probably remember, hearing the words data flow computing. Back in the 80s and 90s, if you walk down the mall, just like today, you hear people chanting microservices, you're going to hear people chanting data flow computing. Well, this was huge. In fact, some universities like University of Manchester were building data flow computers because data flow computing had the promise of bringing a true concurrency in place. Now, over the decades, the word data flow computing quietly died away, and nobody talked about it in year 2000s. And then all of a sudden, in the years past, you hear things that are very different. What are we hearing today? We hear serverless, computing. We hear Amazon Lambdas. And when I hear all of this, I just sit back and, Lambdas, and I, let me try this again, Lambdas. And when I hear these things, I sit back and I just laugh, because what do these things really mean? Well, they are new name given for what we used to call as data flow computing. So all of a sudden, Data flow computing has born again, and it just has a different name. So I want to start out by saying reactive programming, if you will, is really data flow computing. And that's really what you're dealing with. You have a flow of data that are coming in, and as the data flows through, you are trying to perform transformations of this particular data. So the model really is deviating from the CRUD model, where you take the data, but you pass it to a function that you want to work with. We'll call it as a D for data and F for function. And this function, of course, yields a data in return. Now, when you look at this part for a minute, that awfully looks like this, except the data didn't come from a database, and the data is not going to a database. Or I should say, the data necessarily doesn't come from a database. It doesn't necessarily go into a database. But then what we do is we put them into a chain, a pipeline for this computation. So the data flows from one function to the next function to next function through a series of transformations through it. That becomes a data flow computing as a transformation of this data. So in that regard, what are the main essential things in reactive applications? Well, the very first thing about reactive applications is elasticity. Now, what is the reason for elasticity? Well, we all can agree that in the past 10 years or so, what we have done really well in the software world is to make things really elastic, where things can scale up as the demand goes up based on the time or the load, and can scale down when the demand goes down, again based on the time or the load. You know, in my past life, I used to be a system administrator. My job was to take these huge, digital computers, if you will. Some of you may remember the Digital Equipment Corporation, which eventually got bought over by other companies. I used to install those Sun Microsystem machines. Sun Microsystem machines were okay, honestly. They were a little slab, and I was a meager 104 pounds, literally slim. I would break if I sneeze kind of a person, and I would lift these computers and install them. But the DEC computers, monitors were huge. It was a torture on my back to lift them and install them. And I would not wish that on even an enemy today, because imagine today being a system administrator, you cannot possibly keep up with the demands of your enterprise. I was talking to a client recently, and I asked them, on a typical day, how many people use your systems? And they looked at me and said, on a typical day, about 50 to 100 people use it. And I was a little taken aback. I said, you're a multi-billion-dollar company. How could 50 to 100 people use your systems and you could be making that kind of revenue? And they said, you asked us on a typical day. And then they went on to say they're into energy trading business. And in a month, over a 48 to 72 hour time, about 60 to 70 million people use their system. The rest of the month, nobody cares. They're doing a system administrator and setting up accounts, setting up permissions and stuff like that. How do you go from nobody cares for most of the month to there's a 72-hour period window when 70 million people jump on your system? Well, you got to be able to scale, and elasticity is extremely important to survive in that market. Second is message driven. Now, if you really think about what we did in the past, we took the data from the database and then we put it back into the database. Well, the problem with this approach is it binds us to the locality of the data and the format of the data as well. Well, in the data flow computing, that does not make any sense, because you don't want every one of these functional units to go get the data from the database. For one, how do you trigger that data is available? You cannot keep putting a polling to find out if the data is available. You really need to communicate. And further on, I would go to the extent of saying that I have a philosophy that I would like to share. And that is, both in life and programming, we should never share two things. And so what are the two things we should never share? The first one is a toothbrush. I don't think we should ever do this. And the second is a database. So both databases and toothbrushes should never be shared. You know, if you ask me, oh, come on, Venkat, you're too dogmatic about it. Are there times when there are exceptions? Okay, I'll admit, very occasionally, I might even share my toothbrush, but sorry, never my database. But the point really is that you don't want the database to become your bottleneck, both in terms of the format, the communication, the scale. So you really want to favor message driven for that point. So you want the data to flow through these one after another. And that is an essential characteristics of reactive programming is the message driven architecture. Now, the third thing is responsiveness. We all think for some reason speed is vital. No, speed is not the important thing. It's the responsiveness that's actually important. Now, a great example of this, if you will, is infinite scrolling. Now, remember the day you first learned about infinite scrolling. It blew my mind, actually, honestly. The reason is not the technology, but the idea. You go to a website, it's taking time to process to get you the data, and we as an impatient user, what do? We are saying, oh my gosh, the thread is taking too much time. Let me help it. And you hit the refresh button. Now there are two threads running on the server, making things even worse. It cannot possibly lead to better scale because of that. Well, infinite scrolling says, don't take the time to get all the response. A user has made a request. And when it comes to responsiveness, I want to think about these numbers, if you will. Take the number 250 milliseconds. This is the time human beings take to realize that an event has actually happened. So if I wave at you, there's a 250 milliseconds before which you realize I waved at you. That is assuming you're not distracted on your cell phone or looking elsewhere. Now, after the 250 milliseconds, our brain processes this and stimuli and then responds to it. This is the reason why when you drive, they recommend you give at least a 2-second time distance between you and the car in front of you, because the car in front of you hits the brake. It took 250 milliseconds before you were able to register. And now then it takes another 250 milliseconds for your brain to send signal to your leg to hit the brake. And of course, that is assuming we're not distracted. So they want to give us a 2 seconds delay for that processing. And when it comes to half a second, well, that is really when the user begins to notice that they have made a request and the site is taking longer. And 2 seconds is called eternity, and this is not acceptable. Well, for that reason, infinite scrolling like ideas are saying, hey, let's not take our sweet time to respond to the user. Let's get them something so they can chew on. And in the meantime, we can do some processing in the background, and we can keep pushing the results back to the user in streams of this data, either on demand or keep flowing them. And what is the basis for that? It's really responsiveness. And the last thing is resilience. And we cannot really discard resilience, because the application that we will quit using are the applications that are not resilient. Now, as a captive user, as we once were decades ago, where we are employees of a company and we are forced to use their product, well, as a captive user, we take whatever is given to us and nobody cares when we complain. Well, if an application is really poor, it loses data, it crashes too much, what do you do as a user today? You look for an alternative. You don't want to waste your time on a cheap application where the word cheap is not just the cost of it, but the quality of it as well. Resilience is extremely important. This reminds me of an experience I had. I was speaking in a conference, and I also part-time at the university. I've been teaching there for a few decades. But I was in a conference, speaking in a conference in the industry, when a developer came to me and said, hey, Venkat, you probably don't remember me, but I took your distributed object computing course back in 1998, he said. I said, oh my gosh, I remember teaching distributed object-oriented programming in the 90s. Well, so nice to always see a past student. He said, well, I got a story to tell you. I said, oh, I love stories. Go ahead and tell me what you have. And he said, well, I was in your class and we had a group project and we were working on the project. And it was my responsibility to demo the project to the class. So I was in front of the class and I was doing a demo. And right in the middle of the demo, you quietly walked up to my machine and you disconnected the internet connection cable. Well, back in time, we didn't have Wi-Fi. And we disconnected the cable and you went back and sat down and said, continue. Without the network connection, my program crashed and the program failed and I failed the course with it. I said, that's not a story, that's a tragedy. Why are you telling me this today? And he said, well, I wanted to tell you this because you made a difference. I said, how could I have made a difference to you? I feel sorry that I really, failed you in the course back then. He said, no, you taught me an important lesson because that day I learned that I should not program only the happy path. I should really look for failures as well. And then he went on to say, today, he said, when I program at work, on the wall in my office, I have a picture of an evil Venkat, and I look at that picture every day when I code, he said. I don't know how this picture looks, honestly, but I do believe that we should really program for resilience. That is extremely important. So these are the 4 pillars of the reactive programming, and we want to really build for elasticity because scale is important today. We want to program with message-driven architecture because we don't want to communicate to a database as a central mechanism. We want to distributed architecture oftentimes. We want responsiveness because we live in a world of users who have greater demands today, and nobody likes using an application that keeps crashing and loses data. But that brings the question, what has this got to do with functional programming after all? If these are the things we want to build, well, let's go back to what we talked about so far. We can see a couple of things emerge out of this already. You can see that functional pipeline being part of the reactive pipeline as well, instantaneously right in there. So let's go back to this code, if you will. Let's go ahead and comment out those print statements for just a little bit. We'll come back to it. So if I go back and run the code right there, you can see that it actually gives us the result at this point that we obtained. So I'll say var result is equal to, and then we'll go ahead and display the result over here of that computation in the very end of this. So that, of course, we know is functional programming as we used it in Java 8. But however, I'm going to go back to this code really quickly, and I'm going to call this numbers, if you will, and I'll simply say numbers is equal to that particular list that we created up there. But notice what I'm going to do now. I'm going to go ahead and import over here java.util.concurrent.star for a minute, but more important, io.reactivex.star. Well, I'm going to use RxJava here, which is a library created by Netflix for reactive programming on the JVM, but there's a lot of different libraries we could use. But what I'm going to do here is to say flowable.fromIterable. And I'm going to say, in this case, from the same numbers that we had before, I want to create that flowable. So what in the world is a flowable after all? Well, the flowable in reactive programming, so reactive programming is based on the observer pattern. Now, remember, in the observer pattern, which has been around for a while, you have observable. And so you have observable, which is going to push the data, and of course, to 0 or more observers, if you will. So this is the idea that's central to reactive programming, is you have an observable that's going to emit the data that's going to be received by the observers that are interested in receiving the data. But it goes from that point onwards to multiple things. So I can now take that and say dot filter, and I can say sample right there and say is even. So basically, in fact, as simple as I'll just grab these two lines from there and just copy them here. So literally they are exactly the same sequence I brought over. Then I say subscribe. And in this case, I'll say system.out print line, and I'm going to just print it out. And you can see right there is the result of that operation that we got from there. So there you have it, your functional pipeline, as you can see in reactive programming, uses the functional pipeline. So what we are seeing here is reactive programming is really starting out with the functional composition, but plus going back to this code one more time, if you were to take this output and then you were to say, let's say output, let's say done in the very end, when I run the code, you can see all that print, but eventually it says done. However, if I go back again and uncomment those and those, you will notice that it's going to print all those calls along the way. However, one more time, I comment out just the last part in both of those scenarios, both in the Java 8 streams and in the stream right here. And again, you can do this with Java. You can do this with, any language that you want to use. C#, like I said, this was introduced by Eric Meyer as part of Microsoft Research. So you can definitely do this in C# and F# and so on. So, and of course, JavaScript and Python and Ruby and what have you. So the point really here is that when you run this code, you are removing just the terminal operation from both of those. And notice right now, this was giving us a stream. We'll simply say done again over there. And you can see it says done and done, but that execution did not happen. And that execution did not happen as well. And part of the reason is lazy evaluation. Now, based on what we talked about earlier, you also know that functional programming is really based on that. So as a result, we can say that's equal to functional programming, but we also know there is more to it, and we'll see what that more is in a few minutes. And as a result, I want to say that reactive programming is equal to functional programming plus plus. And in other words, you take the ideas of functional programming and you build better abstractions on top of that moving forward. So what are those abstractions? Where do they take us from here? To understand that, let's compare these two. So we will say functional, pipeline, if you will. I'll call it functional streams versus reactive streams. And let's compare these two. There are some similarities. There are wide differences. In function, you have the pipeline operation that you perform. Similarly, in reactive streams, you have the pipeline. Functional streams are lazy evaluation. Reactive streams also have lazy evaluation. Well, unfortunately, the similarity ends right there. Functional composition and lazy evaluation, that's basically where we start in reactive programming. Now, in the case of functional streams, specifically with Java, what are we seeing in this case? You have a data-only pipeline. Well, in reactive stream, data also pipeline. Now, one really troublesome question we often get asked: how do we handle exception, right? So how do we handle exceptions? Well, the short answer is I'm going to say you don't. And the reason for that is that exceptions are imperative style of programming idea. And I'm going to go to the extent of saying exception handling. So exception handling and functional programming are mutually exclusive. So when you look at this, there's a reason why we don't talk about exceptions in functional programming, not because they're not important, it's because they're not really going to sit well together. You can think of exception as fire, and you can think of functional programming as gasoline. Don't bring them together, you're going to have an explosion, literally. So the question is, what do you do with exceptions? Well, I'll answer this question by taking an absolute stupid analogy. A friend calls you frantically and says, I'm in the middle of the freeway, I got a flat tire, what do I do? What's the worst thing you will tell your friend if you don't want to be the friend's friend anymore? You would say, oh, you have a flat tire in the middle of the freeway. I got a suggestion for you. Blow up the freeway and go back in reverse to where you started from. No, you would never tell that to a friend because that's not the right thing to do. Well, but that's exactly what we do in imperative style of programming, isn't it? You call a function, 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 boop, it blows up, and then you go back all the way to where you have a try block. Well, what do you tell your friend? You tell your friend, dear friend, safety is important. Look on both sides carefully. And I know you have a flat tire, but keep driving forward and exit the freeway safely, pull over to the shoulder and get out of the traffic. So you don't tell your friend ever to drive in reverse on a freeway. You ask them to exit safely. Well, that's exactly the point. So what is the point really? So we need to handle the error as data, right? So handle error as data. So error is just another form of data. So it's perfectly okay to have exception. So let it fail philosophy. So what do? So you also have a data channel. So what we do instead is, so in here is oops, right? So not really handled properly in this case. And people invent mechanisms and you really want to deal with it downstream, but you're really dependent on the language and the API to do that. What about reactive programming? Reactive programming gives you three channels of communication. So what are the three channels? The first channel is the data channel. The second channel you have is the error channel, if you will. And the third channel it gives you is called the completed channel. And so you have three channels, so completed channel. So you have the complete channel. So you have data coming through the data channel. Something goes wrong, the data channel closes up and the error comes through the error channel as if it were a data. Now, you don't have any error, but the data is flowing through the data channel. You send a complete signal. The data channel closes to say, I'm done. I'm not going to send you any more data. So you have three channels of communication when it comes to reactive programming. So as a result, if you were to have a problem of some sort anywhere in this transmission, you're going to get that as an exception, but as an error. So where does the error come through? Well, the error is going to come through this. So when you look at the subscribe, there are the three channels. You have the data channel, the error channel, and then you have also the completed channel as well. So in a sense, the way you can write this is as follows. You can say error, and then you can provide a lambda, and then you can say output the error or whatever that you want to do with it. And then a third one where you can output, let's say you are completed, you can say done over there and show that you are completed. So this becomes the nature of that, where you have the three channels of communication. So you have the data channel, you have the error channel, and then finally you also have the completed channel as well that you have in here as the three channels of communication. Now, having said that, of course, moving a little further from this, you can see how it's a functional programming plus. There's more to this abstraction. The first one is these three channels, the data channel, the error channel, the complete channel, that's part of reactive programming. Moving from there, what about, how do we communicate? Well, the first thing is, in the case of a functional stream, typically, especially with Java and C# and how things are done, a single, if you will, pipeline. So on the other hand, you can have a forked pipeline. So in other words, a forked with, if you will, multiple, subscribers. So you can have multiple subscribers are permitted in the case of a reactive stream. Now, in the case of stream-based programming, typically you do sequential versus parallel. On the other hand, when it comes to reactive streams, you often do synchronous versus asynchronous, if you will. That's what we use basically, not parallel in this case. So you're dealing with a synchronous on one hand to asynchronous on the other hand. That becomes the mode of operation. Secondly, in the case of functional programming, it is fire at will, meaning, push. You just keep pushing the data. On the other hand, the one core thing about reactive streams is back pressure. So in other words, one of the key tenets of this is a subscriber, publisher can't ask subscribers to slow down, to go fast or to slow down, and subscribers, if you will. So subscribers can't ask publishers to slow down also or go fast. So in other words, these cannot control each other. So what's the answer for that? The answer for that is to thrive upon back pressures. So the back pressure strategies tell you how you're going to communicate between the publisher versus subscriber. So it really boils down to the following, given these similarities and differences. And what it boils down to is that reactive programming really is a functional composition. Well, sure, plus the use of lazy evaluation. Great. Plus from there, you also have things like, 3 channels of communication where, error as data, right? That's being handled properly. Oh, I forgot to mention one more thing. There is also a communication really very well done. So communication between, if you will, publisher and subscribers. So unlike the observer pattern, where observables keep sending data to observers, in this case, an observable can send a complete signal to the subscriber and say, I'm done, you can go home. Or a subscriber can send a signal to the publisher and say, stop, I don't want this data anymore, be quiet. And of course, the publisher will know not to send the data to that subscriber, but continues to send data to other subscribers that may be present. And then, of course, moving forward from there, code is a structure of the code is the same for synchronous versus asynchronous. This is huge because if you were to program the code synchronously because it's easy and then convert it to asynchronous, that's awesome. You can get performance without losing sanity over the code. And then finally, employs back pressure. So if you notice how the functional programming started out with the same abstraction as functional programming and built on top of it to bring a variety of capabilities. And that is the reason why I often emphasize that reactive programming is really functional programming, if you will, plus. It's really renaming of data flow computing. And realizing that in my mind, I'll be honest, it really helped me to get a better grasp of reactive programming. It also helped me to answer this question for the organizations I work with. And I know when they often ask me, should we or should we not use reactive programming? And that answer becomes a lot more clearer for me when I understand the fact that reactive programming is really data flow computing. And it's really building this abstraction of data transformation with higher levels of abstraction that have been built around it. So in that regard, I would say when I program in functional style, I often think, when I program in reactive programming, I often think of this transformational construct of functional programming, and embracing the ideas of functional programming was really useful for me to embrace the ideas of reactive programming. Having come from imperative programming background for decades, taking the time to learn functional programming. And once I made the transition, and as I was struggling to make the transition into reactive programming, call me silly, but it was almost an aha moment for me one day to sit up and say, oh my gosh, reactive programming is nothing but functional programming plus plus, and perceiving it with that model helped me to really rethink about what is reactive programming, but more so how I would be able to use that as well. I hope that was useful, and I hope that helps you with your journey into both functional programming and reactive programming as well. Thank you so much for being here. Appreciate it.